I welcome you to this lecture where we talk more about ice ages. In the last lecture you learned about solar radiation. You learned all about it, assuming that the Earth's orbit around the Sun is always the same. Okay, you learned that the distance matters, and you learned that the slope angle of a surface matters. Okay, but the Earth's orbit around the Sun is not always the same. There are slight cyclic variations which are called Milankovitch cycles. And we talk about these Milankovitch cycles today because we know that Milankovitch cycles triggered or terminated ice ages. Okay. So I introduced you to Milankovitch cycles in part A, which are associated with changes of the Earth's orbit around the Sun. So in part B, we have another look at ice age cycles. We look at the last glacial maximum, and we look at the extent of glaciers derived from terminal moraine. And then we look at reconstructions of air temperature, CO2, and methane. Let's see what we can learn from that. Okay. Part C discusses whether temperature anomalies led or lagged CO2 anomalies. Which one came first? In the reconstructions, did you have an increase in CO2 first before the temperature changed, or the other way around? In any case, you see that there's a strong link between temperature and CO2 variations. Okay, CO2 is one of the key features. I also introduce you in part C to the bipolar seesaw. Okay, and here you will learn that it's not as easy as you think. If you look at observations, sometimes you get big surprises that you at first cannot understand, but in the end it helps you to understand the entire system. So let's start with talking about Milankovitch cycles. What are these Milankovitch cycles, and what are the timescales of these cycles? So Milankovitch cycles are changes in the orbital cycle of the Earth around the Sun that can explain the initiation or termination of ice ages. Okay, there's a correlation between the timing of these events. Okay, and what we mean by initiation is it's a heat flux anomaly that triggers a warming, and that then sets off a number of chain reactions that we call climate feedback mechanisms that drives the climate into a different state. Okay, and we will talk about climate feedback mechanisms in a future lecture. So, Milankovitch cycles result from changes of three different things. The shape of the Earth's orbit, we call this eccentricity. The angle the Earth's axis is tilted with respect to the Earth's orbital plane, we call that obliquity. And the direction of the Earth's axis of rotation. Okay, we call changes of this direction precession. Okay, these three different types of cycles are shown in this sketch. Okay, you can see the Earth path around the Sun. Okay, and three different type of variations that you get. All right, so let's have a look at the different time scales. Okay, and that's the time scale. You learned what a cycle is. A cycle is a process or feature that repeats, and the time it takes is called the time scale. So let's have one. One is the change of the tilt of the axis of Earth has a time scale of 41,000 years. Okay, the precession has a time scale of 26,000 years, and eccentricity has a time scale of 100,000 to 413,000 years of variations. Let's have a look at these in a little bit more detail. Let's start with eccentricity, the change of the orbit shape. Okay, I start with a little animation, which is a little bit exaggerated, just to get the point. Okay, you can see the path around the Earth can be almost more circular, or at other times can be more elliptical, as you can see here. And with your knowledge about the solar radiation, you can see that if the distance changes, the solar radiation changes. So when the Earth's orbit is at its most elliptic, about 23% more incoming solar radiation reaches Earth at our planet's closest approach to the Sun each year than it does at its farthest departure from the Sun. Okay, it's a big deal. 23%, but not if you average it over the entire year. You get actually only a very small change on the annual solar radiation. Okay, so this is a process that influences the heat flux in particular time of the year. It can be much bigger, it's about 23%. Okay, so currently the Earth's eccentricity is near its least elliptic, most circular, and it is very slowly decreasing in a cycle that spans about 100,000 years. So now the second one is called obliquity. It's to do with the tilt of the Earth axis. And this is why we have seasons. Over the last million years, it has varied between 22.1 and 24.5 degrees with respect to the Earth orbital plane. I show you the animation. You see changes. They're only small, okay, but it can change the seasons. The greater the tilt, the more extreme are the seasons. Larger tilt angles favors periods of deglaciation, the melting and retreat of glaciers and ice sheets. So the Earth's axis is currently tilted 23.4 degrees, or about halfway between its extremes, in a cycle that spans about 41,000 years. Hooray! The last cycle is called the axial precession. And it's about the Earth axis. As Earth rotates, it wobbles slightly upon its axis, like a slightly off-center spinning top toy. The trend in the direction of this wobble relative to the fixed positions of stars is known as axial precession. The cycle of axial precession spans about 25,000 years. The axial precession makes seasonal contrasts more extreme in one hemisphere and less extreme in others. So for each of these precession, for each of these cycles, it actually matters where you are, that the seasons can change slightly, and this can kick off changes that lead into an ice age. Okay, on long time scales, on very, very long time scales. Okay, here's the animation. Okay, have a look at that again. Or maybe another time. Okay, no, not another time. Okay, so Milankovitch cycles. Milankovitch assumed that changes in radiation at some latitudes and in some seasons are more important than others to the growth and retreat of ice sheets. In addition, it was his belief that obliquity was the most important of the three cycles for climate because it affects the amount of insolation in the Earth's northern high latitude regions during summer, which influences melting in that region. He calculated that ice ages occur approximately 40 every 41,000 years. Okay? Subsequent research confirmed that ice ages actually occurred at 41,000 year intervals between 1 and 3 million years ago. However, about 800,000 years ago, the cycle of ice ages lengthened to 100,000 years, matching the Earth's eccentricity cycle. Okay? And we don't still, there's still some things that need to be worked out, but there is a correlation between the timing of Milankovitch cycles and the timing of ice ages and interglacial warm periods. All right, so let's talk about one more point, and that is important to understand. Let's talk about the interference of periodic signals. It's about, actually, you don't only have one factor of influence, you have 2 or even 3 factors of influence if we talk about the orbital cycles. And I just created a very, very basic example for you that you understand the interference of periodic signals. For example, signal 1 is shown here at the top left, which repeats every 41,000 years. Okay? This is just one example of one factor of influence. We have another signal 2, shown here on the top right, which has a periodicity of 100,000 years. And for simplicity, we assume that both signals have the same magnitude. There's no unit in here, it's just called 1. Okay, it's the maximum of both. And now we assume that these 2 processes occur simultaneously and they interfere. Interfering means it's the addition of these 2 signals, and you get something like this. Okay, and just shown here over a time scale of 100 of a million years. Okay, and you can see that there is an interference. At times, they actually sit on top of each other, these signals, and so you get, instead of a 1 magnitude, you get a 2 magnitude. You can see that here. Okay? So this maximum interference, we call it constructive interference, here actually happens about every 400 years or something like that. Okay? There are times where you get a 0 or very small signal, a reduced signal, which we call destructive interference. One has a positive signal, the other one a negative, and they counteract, they cancel out each other. So in terms of the orbital cycles, it's important to understand this interference. They don't all work on their own, they all work together, and at particular regions you get an interference. You get it at all regions, but particular times and particular regions you get the maximum effect due to the interference of these periodic signals. And this interference influences the timing of ice ages. Okay? This interference of signals. All right, this is the end of the first part of this lecture.